So good afternoon, everybody. I hope everybody is awake after the lunch and had their coffees. So I'm Kumar Akash. I'll be presenting our work on classification model for sensing human trust in machine. So you all may have came across multiple of these news headlines recently, especially the Boeing 737 crash or some of the previous crashes as well with the aircrafts. The investigators have found that pilots have been over-relying on these automations and effectively being confused and making wrong decisions and leading to these crashes. Also, the recent thing about self-driving cars, so there have been news articles saying that people don't trust them and may not use them. On the other hand, there are considerations that these automotive engineers are actually over-trusting these self-driving cars. So the trust is a thread which ties all of these new things together. So in this new age of automation, the human trust on these machines has become a really crucial piece. The researchers have came up with the term something called trust calibration, saying that human trust should not be too less on automation to an extent that they don't even use it. So basically the entire benefit of the automation is lost if they don't use it. On the other hand, if they over-rely or over-trust the automation, it can lead to accidents if they trust a faulty automation. So the trust needs to be properly calibrated so as to have the most optimal interaction between humans and machines. However, the way we have been designing machines and user interfaces so far is considering in a one-way interaction in terms of trust. That means the machines have been presenting information so that assuming that humans have to simply read those information and accordingly calibrate their trust. However, as we have been advancing these machines and making them more human-like, it's required that the machines even become human-like in terms of trust. The thing what I'm saying here is, say, when we interact with another person, so between an interaction between another person, so when I talk to you, I try to see you, I try to judge whether you're understanding me or not, trusting my thoughts or not, and accordingly change the way I interact or inform you or the level of information I provide you. So I change those stuff in order to have that interactions better. So what we want is to have the machines, give the machines that capability of sensing human trust in real time and accordingly changing the way it interacts with the human in order to maximize that human-machine interaction performance. So the way we want to do that is in a closed-loop framework. So we want to put human inside the loop at the core, such that we say that the human-machine interaction is at the core, and in a way we can estimate the human trust level. And if we have that human trust level, we can utilize some optimal controllers that can change some of the interaction variables in the machine user interface. For example, we can change the automation transparency, the control authority based on the human trust in order to maximize that human-machine performance. So the crucial piece here is this estimation of trust level. And in this work, I'll be focusing on how we can utilize the psychophysiological signals to estimate the human trust in real time. So the existing approaches which have been utilized for measuring trust typically involves surveys, self-reported behavior to actually understand what the trust is. So this is very good in a kind of offline sense when you want to say evaluate a user interface. But if we actually want to use it as a real-time feedback variable, we cannot keep on asking a human, do you trust me or not? So what we need is a kind of real-time estimation of this human trust. And so that means we need some other kind of signals from human that can give us that information. So when we dig the literature, we found out that people have established such kind of correlations between human trust and some of the psychophysiological measurements. But they haven't been used so far for real-time sensing of trust. So what we will be doing here is using some of the psychophysiological signals to estimate the human trust in real time. So when I say some, we'll be using two of these signals. First is EEG. EEG measures the cortical activity of the brain over the scalp. So it has been classically used in brain-computer interfaces where you may have seen people flying quadcopters with EEG headsets on their head. The other one which we want to use is called the galvanic skin response. So it measures the skin conductivity. So skin conductivity is indicator of the unconscious emotional arousal. So it has been used for measuring stress, anxiety, and you may have seen in movies that they just put 2 electrodes on their hand and use it for lie detector tests. So that's GSR. So we'll be combining these two signals together to utilize for estimation of human trust, and that too in real time. So the key contribution of this work will be the first, we want to establish a human subject study that can elicit different trust changes so that we can use them as a ground truth. And then we'll be developing real-time trust sensor, which uses classification model and utilizes the EEG and GSR signal from the humans to predict the human trust in that case. Sorry. So this will be the basic framework of the talk. So I'll start with the introduction of the data collection, followed by the feature extraction, and then the feature selection and the model training and validation. So let's get started with the data collection, which involves conducting human subject studies. So for the human subject study, we chose a context in which we asked participants that they have to assume that they are driving a car, which is equipped with an obstacle detection sensor. So the sensor will give them whether there's an obstacle in front of the car or not. And based on that stimuli, the person has to choose whether he or she wants to trust that stimuli or not trust. And after that, they will get a feedback whether the choice was correct or not correct. So this was repeated 100 times for each participant, and each participant's choice of whether they want to trust or distrust in each trial was completely based on how was their experience, the feedbacks from the previous trials. So in order to change that trust level, what we did was we changed the reliability of our obstacle detection sensor. So for example, so say one group of participants actually started with first 20 reliable trials. That means the sensor was 100% correct. So we expected that that would elicit a very high trust level in the participants. And this was followed by 20 faulty trials. So we did not inform the participants a priori that the reliability will be changing. But in these 20 trials, the sensor was faulty. That means it had a 50% reliability. So it was basically completely random. So we expected that their trust level will be lowest in this case. And similarly, for the other group, we started just in opposite with 20 faulty trials followed by reliable trials, just to counter any kind of ordering effects. So in order to first validate whether this is eliciting those trust responses, we first collected data from 523 participants using Amazon Mechanical Turk. So we just collected the behavioral responses of what they are responding. And when we plotted the average responses, we actually found out that in the white reliable trials, the actual trust level was very high for the participants. And in the faulty trials, the trust level was low. So basically, this entire study was able to elicit the required trust responses we expected. So we use this as a ground truth for labeling for our classification model. So the next, after the study is validated, we called in participants in lab, equipped them with our wireless EEG headset, which is a 9-channel EEG sensor, and a wireless SIMR GSR unit, which measures the skin conductivity, while they are doing the computer-based simulation of the study. So we called in around 48 participants, all from West Lafayette, Indiana, with varying demographic backgrounds. So after we collected their EEG and GSR measurements while they did the study, we then did the feature extraction. So the feature extraction for EEG considered two types of features. So for the 7 channels out of 9, we calculated both time and frequency domain features. Why both? So when we dig the literature, we find that there's a group of people who prefer understanding the time characteristics of the EEG signal, and there's another group of people who actually study the frequency characteristics like delta, theta, and alpha waves of the feature. So we did not want it to bias ourselves, so we took in all those features which are possible and considered them as a potential variable for our classification model. So for the GSR signal, so GSR signal itself is a superimposition of two signals, the tonic and the phasic. So the yellow tonic signal is a slow moving component shown here, which is basically based on the environmental temperature and all those environmental variables. But what we are interested in is the phasic component, which changes suddenly due to the emotional arousal. So we extracted two features from the phasic component for the GSR. So the further details of all these features can be referred from our paper. So basically, we converted the continuous GSR and EEG measurements into 149 potential variables that can be used for predicting human trust. But not all of them are actually relevant to predicting trust. So the next step for us was feature selection. So for feature selection, for the feature selection, we took a two-step process. The first step was a filter approach, which based on the class separability, reduce that feature set from 149 to a set of 60 features using a relief F algorithm. And the next step was a wrapper approach, which actually chose the best smallest set of features based on a heuristic that maximizes the accuracy of the chosen classification model. However, we realized that there are differences in human trust behavior inherently. So some people may be using, say, different parts of the brain to actually decide their trust decision, but there is also a possibility that there is some kind of general trend between all the participants in the trust behavior. So we considered both the cases. The first case we consider is called the general trust sensor model. So the general trust sensor model selects a common set of features for all the participants. So basically, in order to do that, we divided the participants into two groups. So for the training sample participants, we used their data to actually do the feature selection, and we kept the validation sample participants separately. So we basically used the feature which were derived from the training sample participants and tested it on the validation sample participants to see if these features are being able to generalize for the entire general population as well. So when we did the feature selection for the training sample participants, we ended up with only having 12 features. And these 12 features comprised of both time and frequency domain features of EEG as well as a feature of GSR. The other one, which we call as the customized trust sensor model, is called, it selects a different set of features for each individual. That means we end up with an individual list of features for each of the single participant. So, but we found that on an average, the feature set was much smaller, to only around 4.33 features on an average across participants. And that was expected, because if we want to generalize something to a larger population, we have to consider more different kinds of signal. So that's why for a customized sensor model, which was customized for a single participant, the feature set was much smaller than the 12 feature set of the general trust sensor model. So once we have these feature set, the next step was the model training and validation. So the model of our choice was QDA, the quantitative discriminant analysis, and there was two reasons for selecting that. The first is, in our previous studies, as well as some of the previous researchers have shown that this could be used for predicting human emotions as well as workload. The other thing is the QDA inherently has a notion of probability. So for our optimal controller, we needed that notion of probability to implement those control algorithms. So once we have the feature set and the classification algorithm, we trained classifier for each individual, considering both generalized and the customized feature set. And we did a 5-fold cross-validation to evaluate the performance, and we considered 3 metrics. The accuracy, which represents the correct prediction of both trust and distrust, and the sensitivity, which just predicts what is the correct prediction of trust among 2 trusts, and specificity, which is the correct prediction of distrust among 2 distrusts. So some of the examples of the predictions are, so this is for one of the participants, I just call him Joey, that's not his real name. So for in the reliable trials, we actually find that the classification model was correctly predicting as high trust, and in the faulty trials, it was correctly predicting as low trust. But quite a lot of participants' responses look like this. But some participants, for example, Don here, may not have a very good response, and it was a quite mixed responses. But on an average, what we found out was the accuracy for the generalized trust model for the training sample participants was around 70%, but with a higher specificity, that means it was better at predicting distrust. We tested for the validation sample participants, and we see that these metrics are quite similar. That means the feature set for the general sensor model can be generalized for the general population as well, which is shown by the similar numbers up here. For the customized trust sensor model for the same Joey, we see that the accuracy has increased by 4 around to 94% around, and we have a similar response. And even for Don, we see that the accuracy has increased from 63 to 72%. So in general, the customized trust sensor model has a higher accuracy than the general trust sensor model. But if we see the overall distribution, we see there are people who has accuracy as high as 99% as well. And so there were a lot of people with accuracy more than 70%. So as a summary, so our main motivation is to design intelligent machines which can respond to the changes in human trust, but there did not existed a model which can estimate that human trust in real time. So what we did is to establish a trust sensor model that can use psychophysiological signals, especially EEG and GSR, to estimate that trust measurement. And our classification algorithm was able to have an accuracy for customized model as high as 78% on an average for the entire population. So what's next for us? So our next is basically actually closing this loop. So we have also in a further works, we have also shown that we can even incorporate some of the behavioral responses to estimate that human trust. And we have also in some of the preliminary works have shown that we can actually change automation transparency using an optimal algorithm based on the trust responses, and which actually increase the overall human-machine interaction performance. So this overall framework has been shown to be working to improve the overall performance, and the psychophysiological trust sensor can be even further improve the prediction accuracy of trust and distrust. So I'd like to thank our entire team, which includes me, our colleague Wan-Lin, who is now a postdoc at Stanford, and our advisors, Dr. Neera, Jain, and Dr. Tahira, Reid at Purdue. Thank you.
Great. Let's thank the speaker. And we have time for a few questions.
Hello, thank you so much for a wonderful presentation. I'm Shubhashri, I'm from Syracuse University, and my question to you is the following. So you, if I understood, the data set that you used is based on one simulation, one experiment. So I'm wondering if you're thinking of repeating the simulation, and if the way people are thinking about trust will change across simulations, or if you have thought about that, and how do you think that can vary? And another thing that I wanted to ask is if you find that there are differences across users, so maybe based on demographics or these factors, do you see that there are maybe clusters of users, or do you see some patterns emerging across users?
Yeah, so that's a wonderful question. So for the first part, yes, the trust is dependent on the context in most of the cases. And so this is designed for a particular context, but what we are presenting here is a framework on how you can actually develop that classification model. So this entire framework can be simply extended. You just need to conduct a new study, have that data set, and extend this framework on collecting the data and finally getting that classification model. And yes, each person based on demographic have a difference. So in one of our previous work, we have already shown that like simply males and females, or say difference between countries, have a kind of different rise and falls of trust behavior, which we saw. And since our classification model is like the data is trained for each person, what we are selecting is just the features which are relevant for trust. So we are generalizing the features, but yes, you need to train a different model for each person based on the training data. Thank you.
Hi, Daniel Abrahami from FXPAL. First, I have a quick clarification question for you. Did I understand correctly that you used the same data first for feature generation, and then you used the same data again for doing your training and testing of the model?
Yes, for the customized, for the generalized model, so that the 32, so the 2/3 of the participants' data was used for feature selection, and the 1/3 of the participants, they never saw that data was not used for feature selection, but the selected features was then misused for training a new classification model for the validation sample participants, and basically generalizing that, whether that can be
and that included the participants whose data was used for the feature selection, correct?
So So this one, so these are the participants whose data was actually used for feature selection, and these are the metrics for the participants whose data was not used for feature selection.
Okay, thanks.
Okay.
My second question is more kind of meta. So you said correctly that GSR has been used to measure stress, to measure lying, to measure trust now.
Yeah.
Do you think that the signals that we get from GSR, you know, all of us working with sensors, actually encompass all of these constructs like trust, stress, lying? Or do you think we're actually measuring one thing and we're just each of us calling it the thing that matches our paper?
Yeah, that's definitely a good argument. But so for the trust, so what we are considering here is trust. So trust as a construct is not simply a very simple thing, say as a workload. It's a combination of multiple things in a particular context. So depending on the context, depending on the situation, the trust can vary. So depending on the, even say workload, your trust on the system can change. So what we are not saying that exactly, so this form of GSR is equivalent to this form of trust. No. So for a given context, if we train the classification algorithm, if we use this feature along with the things in the EEG, yes, we can predict trust. We found that if we just use GSR, no, we cannot have that prediction of trust that accurately. We need to use that multimodal combination of these signals.
I think that part is build on that. I think that point, would we be able to show some level of context independence that's viewed as a future goal? You know, if we could identify certain psychophysiological sensors that truly seem to have across different contexts some tie to trust or other things that people are interested in, I think that would be valuable. But also just we can't say any more than what we show in this context.
Yeah, but this is another criticism of your work. I think
Yeah.
it's kind of a question for the field.
No, but that's a very good one, because you're right. Trust is a word that's getting thrown around a lot in a lot of different contexts, and we all have to be careful about what we're really defining.
I have one final question, and I know there's more questions, but each time come up
Yes.
after this session and present.
I find the whole concept of closed-loop trust tuning to cast the ethical question of trust and human trust and automation in a very interesting light.
Yeah.
You, after all, are adjusting to the human's trust level, but you are, it's right for you to manipulate that trust level. And so how should we use this capability you provide?
Okay, so that's a good, that's the question we have been thinking for a long time, and what we came up with. So if we see the major thing for the way we designed the controller is to maximize the human-machine performance, not change trust to say a fixed level. So we have done some future work after that. As basically we do not manipulate the trust. Say we want the trust to be very high or we want the trust to be very low. So our optimal controller is designed in a way with a cost function such that the overall the entire interaction performance is increased, and that may require, say, increasing trust or decreasing trust. So for example, we found out that effectively what happened was, in a more riskier situation, the automation wanted to reduce the trust so that the human can think more and decide better, versus in a more less riskier situation where it was more confidence on the automation itself. It itself means the optimal controller was found to be increasing trust in those cases. So it depends on how we design our controllers.
If you as a designer
Yes.
can accurately assess those contexts,
Yes.
then you're great.
Yeah, so we wanted to understand that, and we did that. Thank you for the question.
Okay, let's thank Kumar one last time.
Thank you.